problem reads, we have a point charge Q1 with magnitude 2.40 microcoulomb is held stationary at the origin. So to visualize this problem, you have like this one. This red dot that you are seeing here is your positive 2.40 microcoulomb, and it's located at the origin as is stated by the problem. And you have a second point charge Q2 with a magnitude of negative 4.30 microcoulomb moves from point x is equal to 0.150 meters and y is equal to 0 meters. So to visualize that one, if from your origin you measure 0.150 meters towards the positive x and y is 0, so meaning it lies on the x-axis. So this is your initial point. We will name that point A. This is where your Q2, which bears a negative sign, is initially situated. Now, according to the problem, it must be moved to the point x is equal to 0.250 meters and y is equal to 0.250 meters. So you measure x is equal to 0.250 meters along the x-axis and also along the y-axis, and the intersection of that measurements yields your position for the point B. So this is where your point A, your Q2 charge, will move from A to B. The question is how much work is done by the electric force on Q2. So some measurements that you should take into consideration is that from Q1 to Q2 at point A, we will call that RA. From Q1 to Q2 on point B, we will call that R sub B. Alright, now looking at the geometry of the problem, we want to recall first something that is essential for us to understand. Alright, so this is just a visualization which tells you that the electric force will do work on charge Q2 to move this charge Q2 to the position B. So recall that according to the work energy theorem, particularly on the relationship between your network and the potential energy, the net work done on a system is just equal to the negative change in the potential energy. So equivalently, if you are going to rewrite that one, you get that the work done in moving specifically the point charge from point A to point B will just be the difference in the potential energy at point A and point B. This is telling you then that you need to solve for the potential at point A and potential at point B so that you can get the network that the electric force must do. And recall that your potential energy simply is K, Q, the charge 1 or the source charge, and Q sub 0, the charge 2 in this case, divided by R. So this is your potential energy equation, and this is very similar to your electric force. The only difference is that the R here is not squared for the potential energy because in the electric force, the R is squared. Anyway, moving on, we do understand then that we need to solve for the potential energies. Specifically at this point, we will solve for the potential energy at A. Now recall that the equation will just be K, Q1, the source charge over here, and Q2, the charge at the position A, divided by RA. Now it's very clear in the problem that your RA is just 0.150 meters, so you just have to substitute the values. And another thing that you should note, there is no absolute value between Q1 and Q2, unlike your electric force. That means to say that your UA or UB could take a positive or a negative value depending on the sign of the charges. So as you can see here, I meticulously write the corresponding sign of the charge. Q1 is positive 2.40 times 10 to the negative 6. Your Q2 is negative 4.30 times 10 to the negative 6. And RA, I would like to emphasize that this RA is not any arbitrary distance R, but that should be the separation distance between the two charges. So in this case, your Q1 is at the origin and at point A, where your Q2 is initially situated, they are 0.150 meters apart. So that is why your RA in that case is 0.150 meters. Now, when you do your calculation, you end up with UA is equal to negative 0.6192. I just rounded it off to the 4 decimal places. Newton times meters, because if you notice, Coulomb and Coulomb here will be C squared, and in the value or units of K that will cancel out. So I am left in the numerator Newton meter squared, and I have meter here. So 1 meter cancel out. So I have Newton times meter. And recall from your previous physics that Newton times meter is the unit of joule. And take note, this is a potential energy and we're seeing joules. So this is really a good sign that we're doing it right, because your energy is in terms of joules. But notice over here, another thing, the potential is actually negative 0.6192 joules. So we are done with the potential at A. Now we need to solve for the potential at point B. Looking at the equation, the first thing that you will get to see is that your RB is the separation distance from the source charge Q1 to the new position of your Q2 charge. And this is your R sub B. Now, I'm hoping you do realize that this is not directly given in the problem, so you are going to use Pythagorean theorem to find for R sub B. Alright, now working with R sub B, I just simplify the illustration over here in terms of the corresponding lengths. And recall your Pythagorean theorem, which says that RB squared, in this case our hypotenuse, is equal to the sum of the squares of the individual legs. Our individual legs along the x is your 0.250 and also 0.250 along the y. So if we're going to solve for the magnitude of RB, that will just be the square root of a squared plus b squared. And as I've said, we just substitute the values that I've mentioned earlier. So 0.250 meters squared, so you can think of it as the measurement of the legs along the x. And b squared would be the measurement of the legs along the y, which is 0.250 meters also. So when you calculate that one, you get the square root of 2 of 0.250 meters, or in decimal point, that is just 0.3536 meters. So we have now solved the separation distance from our source charge up until the new point B, and that is this value, 0.3536. That means to say then, of course, we move our charge from A to B. That means to say that we are now ready to solve for the potential at point B. So you just substitute the values and make special consideration that you bear whatever sign the charge has. And RB is 0.3536, which we just solved earlier. So you get that the potential at B is negative 0.2627 Newton times meters, or negative 0.2627 joules. And if you recall, if you remember the values, this is actually a larger value than UA, and I will explain the significance of that later. Okay, so recall that we need to find the work done that is being done by the electric force on Q2 as it moves from A to B. And according to our equation, that is just the difference in the potential energy at A minus B. So we plug in the values that we have solved and take special attention of the sign. So we get that the network is actually negative 0.3565 Newton times meter, or negative 0.3565 joules. And this should be expected na mag-get taog that we can get a negative charge. And I will explain the significance of this as I've said later. Now, I want you to recall something about our class and recall the analogy of in gravitational field about the potential energy. So if the boy will let the ball fall, so the normal behavior of the ball under the gravitational field of the Earth is to move down towards the center of the Earth. And we know that the potential in that case is negative, right? But in terms of the work, or the potential decreases. But when we're talking of the work done in this case, work done by gravity on the falling ball, the work is actually positive and the potential decreases, right? But in our case, if you notice, the work done in moving the charge from A to B in this case, as we have solved, is actually a negative work. And if you remember, if the work is negative, you must expect an increase in the potential energy. So that means to say you must expect that the potential energy must increase as your charge is moved from point A to point B. Now, if we go back over here to our calculation, let's see if that is correct. The potential at A that we have solved is 0.6192. The potential at B that we have solved is 0.2627. Now, since these are negative, the more small the number is, it actually has a larger value. So this is true. You notice that the potential at point B is significantly larger than the potential at point A. And we should expect that in the sense that we're actually getting a negative work. And remember, our analogy in class, if we're getting a negative work, if we're doing a negative work, the consequence of that is the potential energy increases in that case. All right, so just like when I'm going to move this ball from this position up until here, notice that the red laser that I'm moving from here to here, I will be doing a negative work because my displacement is going up, the force is going down, so negative work. But notice that the MGH, the gravitational potential energy in that case, increases. So that is why when we try to think again of the answers that we got, this is actually a correct answer because we're noticing a large potential at B than the potential at A. And that should be expected because the electric field actually does a negative work. And if we try to recall with our discussion, we should be expecting that the potential energy must increase from point A to point B since we are actually forcing the charge to move against its natural tendency. Take note that this is a negative charge, so its normal tendency, just like this ball, the normal tendency of the ball is to move towards the ground of the earth or towards the center of the earth. And for this charge Q2, its normal tendency is actually to move towards the positive charge. However, since we are forcing it to move against its natural tendency, that can only be done when we increase its potential energy. And I'm hoping that this clarifies our discussion in class.